Finally, as promised, we're getting on with Chapter 14, talking about different cooking methods and some of the utensils that we'll use. Food service, in the context of Cal Poly's program, is focused primarily on food that's prepared in institutions like hospitals, prisons, schools as a subset of that, both elementary, high school, and preschool. The retail and restaurant world is one we don't spend quite as much time on, but really most of the principles that apply in institutional food service also apply in a retail setting. And finally, in business and industry, most large organizations such as Google and Hewlett-Packard and Ford Motor Company and General Motors oftentimes will have an on-site, or sometimes they're called in-plant, feeding program. And so food service principles can apply in those settings as well. We're going to talk about small equipment and large equipment. And the hope is that after we've talked about this and you've done the reading in Chapter 14, you'll be able to describe two browning reactions, talk about the different and appropriate heating methods for different types of foods, that you'll understand and be able to recognize different kinds of professional kitchen tools and equipment, have a better understanding of how to choose and care for knives, and also have a better idea of how a professional kitchen is organized. So that first reaction, and I know we touched on this when we had our very first quiz, is caramelization. And caramelization is exactly what we talked about previously. It's the browning of sugar. It's the very simplest browning reaction. It takes very high heat, and it does result in a favorable flavor change. Sweet, sour, bitter, fruity, the butterscotch, caramel, nutty flavor that we like in a caramelized apple or in peanut brittle are examples of those flavor changes. And generally the color changes from white to clear to yellow to brown, and we'll see that at the end of the quarter when we actually make peanut brittle. The Maillard reaction occurs in foods that are not primarily sugar. Mostly we think about it in terms of meat, but it also occurs in items like bread crust, and in some vegetables. It's where you have a carbohydrate molecule, an amino acid, can be a lot of amino acid or just very little, plus heat in the absence of moisture. So my symbols on the slide are carbohydrate plus amino acid plus heat minus moisture. Generally these foods are dry, or if it's a meat item, it's at least padded dry, so there's not excess moisture. The amino acids contribute to the interesting flavor, and these present more complex flavors than what we see in something that's just carbohydrate. As I said, browning occurs at a very high temperature. It requires high energy and movement of the molecules in the food, and most foods that we know of brown only on the outside as a result of the evaporation of moisture by heat, the application of heat, and in turn the browning that occurs. Water, as you know, boils and vaporizes at 212, and that's why steaming or boiling isn't hot enough to get foods to brown. But the illustration on this slide of a steak that's been placed on a grill or a broiler is a great example of a food that browns at the high heat that the exterior is exposed to, and yet because of the amount of time that the food is exposed to heat, it remains juicy and moist on the inside. There are some risks associated with browning. Dried fruit, if they're not treated in some way, can not necessarily spoil, but they don't look as appetizing. There's a very slight reduction in nutritional value because of some amino acid destruction, although here in the United States we have an abundant protein supply, and so normally that's not something that we're concerned about. Probably the most significant thing that we hear about is the formation of acrylamide, which is a byproduct of this combination of sugar, asparagine, and very high heat that occurs usually grilling, high temperature frying, and that's why we recommend that those foods would only be consumed occasionally and not in large quantities, and that you would also include a variety of antioxidants in your diet in order to temper or help to mitigate the consumption or the formation of acrylamide. We also do cook foods using moist heat, and the examples here on this slide are some fish that's being poached as well as some beef stew. These foods generally are pale in color unless you brown them first. If you do brown a food first before you add the moisture, that adds the complexity that we just talked about with the Maillard browning. If you cook food without browning, it tends to feature or enhance the intrinsic or the natural flavors that are within the food without adding any new flavors to it. This slide gives you a sort of a condensed version of some of the different ways that heat is transferred, and I apologize that the word conduction is kind of blended in with the word heat, but the top left corner represents conduction, where heat touches a pan, the pan then gets hot and conducts heat directly to the food, and that's what causes the cooking of food in the pan. Convection is where the movement of the medium surrounds the food. So in the image, it's the movement of water in a pot that's cooking broccoli. It could also be the movement of air in a convection oven like we have in lab, where the fan is circulating the air and the air is surrounding the food. We can also have radiant heat transmission, as you see in a grill or in a broiler. Generally in a grill, the heat's coming from below. In a broiler, the heat's coming from above. And then we have microwave transmission of heat, where the actual moving of the molecules in the food cause friction and cause the food to warm up. This is an example of conduction. The pancakes on the griddle or the pork chops in the pan. Certain materials are better conductors than others, and metal is generally the best conductor. We can also have heat conducted through air and steam. There's also conduction that happens within food, where the heat travels from the outside of the food to the center. And I put on here a picture of a prime rib roast. Great example. You put it in the oven at 350, 400 degrees. It starts cooking from the outside, and then over time and slowly, the heat conducts through the muscle of the roast. It is variable depending on the thickness of the meat, and because something is twice as thick doesn't necessarily mean that it's going to take just twice as long. When you're cooking or roasting meat, chicken, poultry, it's something that should be monitored with a thermometer